We are putting reflector satellites in space to shine sunlight onto solar farms after dark.
If you have an enemy that you really want to annoy, you could really
Yeah, we get that question a lot. Is this going to be a death laser? We really are prototyping a new form of energy here. It's like building a new nuclear reactor or something like that.
Hey, Ben. Welcome to the show. Why don't you tell us a little bit about what you're building?
Yeah, glad to be here. We are putting reflector satellites in space to shine sunlight onto solar farms after dark. It's kind of like the quick pitch. The longer version is where the whole world is gearing up to solve clean energy on a global scale, and there aren't really a lot of great solutions to do that. We're still burning an awful lot of fossil fuels, and there isn't really anything stepping up to come in and bridge that gap. Nuclear power is, a bit too expensive and a bit too slow to scale. Fusion is way off in the future, and we can definitely get into talking more about that. And wind and solar are just variable loads. So because of the variability, you have to come in with batteries in order to solve that problem, and batteries are pretty expensive. So we come in with this new solution, and we're like, why use batteries if you could just have more power all the time? Why not shine sunlight on solar farms and power them up after dark so that they can be our only supply of energy? And that's basically what we're doing here today. In the future, we're just building a bunch of reflector satellites and putting them in the right orbit and shining them down onto solar farms, right after sunrise and right after sunset, and before sunrise. So we can be in a sun-synchronous polar orbit over the Terminator, and that means we're always flying over new solar farms at that most valuable time of day, when peak demand goes up and everybody gets home from work. They plug in their electric car, they start using the stove. That's when we're in the sky. We'll fly over, shine sunlight down, and convert that sunlight into energy.
I love it. So you guys, because you used to work at SpaceX, right? So you heard the concerns about Starlink, like shining too much light down. You were like, let's do more of that.
Yeah, but let's get it in exactly the right spots. So that's the whole thing, is doing it very precisely. So you have to make sure that the mirrors are super flat, so you hit a really small spot from orbit. Our satellites we're able to aim them very well. So if we're flying over a place that doesn't want to receive sunlight, we just point the other way and shine sunlight right back into space.
Or if you have an enemy that you really want to annoy, you could really make their house light at dark. No.
Yeah, you could light them up. We get that question a lot. Is this going to be a death laser? The answer is no. It's very difficult to actually get enough power on the ground where you could do any damage. We're going to be significantly dimmer than sunlight for a very long time. I think that's a very easy concern to have, but it's not going to be real with what we're building here.
Fair enough. Cool. Well, let's take a step back. I think that if people are just hearing that for the first time, they're like, I just heard a lot of words that I have no idea what they mean. So that's the joy of this podcast, so that we get to dive deep into them. So people might know I actually work at a satellite company. So I work at Astronis. We build communications satellites. Before I joined, I really knew nothing about this. But when I got to Astronis, I had to learn about it. I had to learn about how do you build a satellite, how do you keep it in space, what are orbits, all those things. So I think let's dive into basically all of them. Maybe as a frame, I'll tell people generally in space, we think of things as buses and payloads. Like those are the two parts of a satellite. The payload of a satellite is what it's doing. So in my case, the payload is a communications radio. It's just a thing that passes communications that go up to it down to a new spot on Earth. But for you, the payload is different. The payload is the big, gigantic mirror, which is focusing sunlight and pointing at a particular spot on the ground. There's also a bus. So the bus of the satellite is basically everything that's needed to support that payload. So it's everything from like thrusters if you're going to move around, but I don't think you have those. So we'll talk about that in a second. It's things like a flight computer. There has to be something that tells everything else what to do. It's the way that you point the satellite. It's the physical box that the satellite is contained within. All that counts as the bus. So I think for the sake of this conversation, let's divide it into payload and bus just to begin, make it simple. And so let's talk about the payload first. Tell us about this super cool, gigantic mirror. Like how big are we talking? What's it made of? Tell us more.
Yeah, so we can start out with a 10 meter by 10 meter reflector. And it's basically just a piece of Mylar that we launch into space. The thing deploys out, and then it's just a very large reflector. So you can see here's a little piece of it, and it's pretty shiny. We're just doing a really large version of this. And the Russians actually did this in the 1990s with this thing called Zenemaya. It was like a 20 meter by 20 meter reflector. That thing deployed out, it was super wrinkly, but it did do a reflection from orbit, and that worked out quite well. We also see solar sailing vehicles using these kind of reflectors. NASA's launching this mission called ACS-3 pretty soon, which is, a 10 meter by 10 meter reflector. It's going to deploy out, and they're going to actually use that to solar sail around and actually raise their orbit. We're making them a little bit more reflective, pulling them a little bit tighter, and that allows us to, shine sunlight down and convert it into energy. And yeah, it's kind of like the simplest payload that you could use. I think it's a lot simpler than a telecommunications radio, for example. So, Starlink or a Astronosis system, you're sending a lot of data down. So you need very, very good antennas, and you need a lot of processing in order to send that data down. We are just using a very simple structure. And I think that's a huge feature of this, is it's kind of like the simplest thing that we could possibly launch into space. And yeah, that just makes the entire system so much cheaper, and able to scale up a lot faster. And we're going to be able to make a lot of these. And then the other piece of that, the satellite bus itself, is also going to be very simple, because we're a very small vehicle, and it basically just has to point pretty accurately, and be able to move around. It's one of the simplest satellite buses you could have. We're able to use very simple satellite buses, very lightweight. And yeah, that's a huge component of why this is going to work. You don't want energy equipment to be very expensive. You want to be able to make something that's going to scale very well. You want to be able to fill up an entire rocket with these vehicles and have that not cost too much money. So yeah, that's what we're able to do with this.
So tell me about the reflectivity basically of this thing. So is it just literally, so what is Mylar? Start there maybe, and then talk about how reflective it is.
Yeah. Mylar is just a thin plastic, and you can use polyamide, you can use any other material. And then what you do is you illuminize it in a vacuum chamber. It's basically the same exact thing that potato chip bags are made out of. You can kind of think of it like that. Like the inside is very shiny, and it's just a very thin plastic. Now, a lot of people are really worried about the reflectivity of our satellites. They're like, oh, I see those solar sail vehicles. They look terrible. They don't look super shiny. It doesn't look like a very good mirror at all. And I think there's a lot of, kind of concern about that. Like Zenemaya was super, super rough. The interesting thing is it's actually not that hard to make a really good mirror with Mylar. We actually have one right here, and you've been looking through it this whole time.
No way. That's so cool.
So I have a 45-degree Mylar mirror rigged up, and yeah, we're actually looking through that right now.
Wow, that is the coolest demo. If people who are not watching on YouTube, you have to go check that out. Literally, this whole time, I did no idea. But now I can see it, because I can see, wow.
Yeah, so that's Mylar. And it's just
That's brilliant.
It's like 90% reflective. You lose almost nothing in it. And you can make it very flat when you're able to pull it tight enough. So that's all we do. We pull it a little bit tighter, and we get a very good reflector.
That is awesome. Well played. What's the... so talk to me about, so I think that at one point you were doing collimators instead of just like a sheet or something. Is that true? And why did you decide to go with just a mirror instead of like a fancier, like parallel beam thing?
Yeah, so the original thought behind collimators, it was really based in analysis. So I was doing a bunch of Monte Carlo simulations on how many solar farms were out there, and with different configurations of satellites, how much power is getting to the ground, how much money are you making with them, and all of that. And in the data, there's a lot more small solar farms than there are very large solar farms. And when you do the optimization curve out, you can make more money if you can serve a 500-meter solar farm or smaller without spilling light into the environment. And yeah, so I went about designing a system that's actually able to achieve that. So this is basically a bunch of small telescopes in parallel that takes in sunlight and then outputs collimated light. And then you can reflect this down to the ground, and you get a smaller, sharper sunlight spot on the ground. Now, that is, in the very deep future, that's definitely the way to do things. When you need to serve, a very large number of solar farms and you're kind of like maxing out the market. It turns out early on, you actually don't need this. And it's kind of interesting. So this made a ton of sense over just like a very large flat mirror, which is kind of like the traditional way that people have looked at space solar. They're like, oh, you put like a mile-wide reflector up there in low Earth orbit or whatever. And then because of the angular size of the sun, it spreads out on the ground. And, you have to make it really big to get any power to the ground. So then this came in and fixed that. So you can get a lot more power to the ground in a very small area. But in doing the math for this, we basically had a bunch of flat mirrors behind it. And when you reflect off the flat mirrors behind it, you get the collimated thing. But then at that point, you're able to delete this from the math, and you just have an array of smaller flat mirrors, which is essentially approximating a parabola. And if you just look at that, it's actually way better than even the collimators. So it's kind of this like third stage of design that we discovered in doing the math for this and looking at this, where it's like, actually, you don't want a big flat mirror. That's stupid. We knew that from the beginning. That scaling is terrible. With the collimators, the scaling is a lot better. But if you then delete the collimator and have all the small mirrors behind it that are doing the focusing, then you end up with this other curve that gets way better performance than the flat mirror, but is actually a lot cheaper than launching these things up. And you still have a very large market because there's so many giant solar farms out there. So you're able to serve them, make tons of money, and until the point where you're making like tens, hundreds of billions of dollars a year, you don't need collimators for a while. They're definitely something that we're going to be adding in the future. So it's a piece of technology that we're going to continue to develop, but it's not something that's required for our initial constellation, which is great because it makes the lift a lot easier. It's a lot easier system to build when you're just making large flat reflectors instead of these collimating optics.
Very cool. So tell us, just take like the one step more beginner on what both of those things are really quick. So talk about, what is a parabola, or like why does a parabola have the cool special property of being able to focus things? But then also like, is a collimator just basically a laser? Like, is that the simple way to think, like purely parallel light coming out of something?
Yeah. Collimated is just laser light. So it's just like, taking some light that would spread out like this and making it more like a beam. So that's essentially all we're doing with this. A parabola is very good at that. If you think of like an antenna, like a Wi-Fi antenna or something like that, where it has the big grid, your source is kind of like a circle that's coming out, and then it hits the parabola perfectly so that everywhere it hits here converts into just a straight beam. So you're kind of taking this thing that would spread out and converting it into this straight beam that goes across. And with this, it's essentially taking the sunlight, which is coming in at this big angle, and it's blowing that out and converting it into light that goes more straight. The problem with doing that is you lose a lot of the area. So there's very small inlet holes and very large outlet holes. So you're essentially blocking a lot of the light that would be going right through in order to collimate it. So, a laser starts out very small, and then you have like a big telescope in order to direct in one direction. You kind of have to pay the same toll with the collimator tile. So you're losing a little bit of light there. And you make up for it by transmitting over a very long distance. It's kind of like high voltage transmission lines for electricity. But it is expensive to do that. It's expensive to have that high voltage transformer there. So a parabola is really interesting because it's kind of like the perfect curve. Like if you look at it on a graph, it's like, it starts in one spot and then like all the little light rays that hit it like go exactly straight up, which is a really cool thing. And a lot of people ask us like, why don't you use a parabola to focus the light onto the ground? And it's not what you want, because there's a problem with using a parabola, which is, if you're trying to hit a spot over here from, the sun that's over here, and your mirror is moving, you always need a different shape parabola in order to reflect the light and get it collected over here. So the parabola, like the curvature of the parabola is always changing. It's very hard to make a parabola that changes. Like, the James Webb Telescope parabola, they're able to change those, but you don't want to have to do that.
On the fly while orbiting every single orbit.
Yeah. Like, and all the time. But what you can do is you can use a bunch of small mirrors, and if they're all like, working in parallel and you're able to aim each one individually, you can approximate a parabola with a bunch of these small mirrors. And that's what we're able to do with our constellation. So, if the sun's over here or it's over here, like we have a bunch of little parabolas that are all in sections, and as they all move around, they're able to all rotate at exactly the right rate in order to approximate a parabola as a whole constellation. And it's
but
really
not as an
similar to
individual
condensed solar
satellite,
farms.
right? Like, but not as so each individual satellite is just one sheet. It's not many smaller sheets like the James Webb. You're saying that the system as a whole is approximating with many satellites. It's approximating a parabola.
Yep. Yeah. And each satellite is just a flat piece of that. Yeah. And it's really like a condensed solar farm. So if you see these solar farms out in the desert, where they have all the mirrors in the field, and then the salt tower up there, it's a bunch of little flat mirrors, and they're all kind of approximating a virtual parabola. As the sun moves around, they're all moving at different amounts, and they're all focusing light onto a central point. So they are approximating a parabola, just with a lot of small flat mirrors, and kind of an interesting configuration. Like the parabola is like, scaling constantly, and like wherever it touches one of those mirrors, it's, that's where they need to point.
So I think people would be interested to hear about how small it gets. Like they might hear 10 meter by 10 meter thing, like, oh my God, it's the biggest satellite that's ever launched. Yeah. Like, oh, how do you even get that up there? How do you fit that in a rocket? But I think people would be surprised to learn that it's not just that way when it gets up there. It actually has to deploy. So do you want to talk about how the deployment happens and how small it packs into to be in?
Yeah, you can pack a 10 meter by 10 meter reflector into something that's about this size. So this is, and it's not even just us that's doing that. It's like NASA ACS-3 solar sail vehicles will be 10 meters by 10 meters, or 9.9 by 9.9. But yeah, they pack into a 12U CubeSat, which is this big. So, we can go to like a 16U CubeSat, and, we'll have no problem launching, thicker material, thicker booms, all of that, for a little bit extra mass. So it's, very much like, you do kind of the tape measure trick, where the boom is deploying out, and then, it brings the reflector with it. And that thing can cover a large area. We do have a couple tricks to keep the mirror a lot more reflective. Usually when solar sails are packed up, they're folded in 2 dimensions. And when you do that, you get creases because you have to bend it over a very sharp radius. You get super high stress there and it plastically deforms. And then even when you expand it out, you still have those plastic deformations present. So what we do is we can do tricks where we basically unroll the thing. So we don't have to 2-dimensionally fold it. And that's very helpful. And that keeps the mirror a lot nicer.
That's very cool. I saw the one that because Bill Nye made one of these, right? Like the Planetary Society did.
Society. Yeah.
Yeah, I saw that one, and it had all the little creases in the side. He had this really great image that he gave, which is like it packs into the size of a loaf of bread, and when it expands, it's the size of a boxing ring. Those were his 2 benchmarks. So you got to come up with your benchmarks. I don't know what that thing's like a small heater or something, and then it gets massive. How big is 10 by 10 meters? It's like, what's it, something roughly that equivalent? Who knows? And,
it's 30 feet by 30 feet. Yeah, it's very large.
Yeah, totally. So talk about it. The only way that's possible, though, is because the Mylar is so ridiculously thin, right?
Yep.
How thin is your sheet?
It's 0.001 millimeters. You can go a little bit thinner. We're still playing with that a little bit. You want it to be as thin as possible, but you don't want to lose the reflectivity.
Yeah, don't let it deform. So like a heavier thing would be better to resist deformation, I guess. You probably also want to, is this a thing? So, solar sails, we'll talk about that in a little bit, about how you're actually, using the sun's photons basically to fly. But is it true that it would like buckle or like bend out in the same way that like a ship's sails would when it's getting pushed on? Like, do you have to worry about that sort of deformation?
Yeah, you get a little bit of billowing. The way you solve that is with extra tension. So usually solar sail vehicles don't have very much tension in the sail. We're going to be putting a bit more tension in our sail in order to keep it reflective. And as long as you have enough tension pulling this way, it's not going to billow too far this way. We do also have a couple of tricks that we can do to move the end point of the arms, and that'll allow us to basically go back. So you can preload it in one direction. So when the radiation pressure pushes on it, it doesn't move it around. And cool. It stays flat. And there's a tolerance on the flatness. So, we want to stay within like a 5.4 kilometer spot on the ground. So it's not like it has to be perfectly flat. As long as it doesn't move so far that the light blows out of the spot we're trying to hit, it's not an issue.
Totally. How do you think about the size? How did you determine that 10 by 10 meters was the right size?
Yeah, the size is driven a lot by what's possible to manufacture, and what you're able to get to the ground. So you don't want too big of a reflector, because then you're basically getting light from each side of the reflector on the ground, and it makes it that much further apart. So, when other people look at this, they're like, oh yeah, we want a kilometer diameter reflector. That actually makes your spot size on the ground a kilometer larger. So you're losing a lot of irradiance when you do that. So you want it to be small enough that the light from each edge of the mirror, is pretty close together. But then you have to balance that out with the fixed cost of the satellite. So, you have to have like a flight computer, all the avionics, like the actual satellite bus, you have to pay for that. So it's really the balance of, making the mirror performant, like the smaller the mirror, the better, balanced with how small can you make a satellite bus, before the thing starts getting too expensive. And you do get a lot better scaling, with the area, because it's area squared, and satellite bus is 1 unit. So you have this like, there's a couple of terms together in the optimization, but it works out pretty simply with just like, these are the fixed costs of the vehicles. These are the, the cost of making the thing larger. This is how much power you get to the ground. You just kind of do that math out. You plot a curve, pick the best point. The ideal like end state kind of scenario is like 54 meters by 54 meters. You never really need to go much bigger than that, which is pretty cool to see. And yeah,
it's pretty big.
Yeah, that's very large. That's like the similar to the size of the International Space Station or something like that. We haven't built anything like that. But the 10 meter by 10 meter is like half the size of, what the Russians launched in the 1990s. So, we're pretty confident that we can pull something off that's a lot smaller than what's been launched previously.
So one final question about the mirror before we go on to other parts of the satellite bus and talking about the vision of the company and things like that. Tell me about meteoroids or micrometeoroids. Like, are you worried that with this huge area, you might get poked to death by little tiny rocks flying through space?
Yeah, I mean, micrometeorites are definitely present in the orbits that we're going to be sitting in. You can look up. There's a couple books on orbital debris, and there's some great graphs in these books. So I just got to calculating like exactly what the risk is. How often do micrometeorites of what size hit your vehicle? And I just kind of like did the calculation like per square meter, like what's the actual area of that. And then once it spreads out, like kind of how much damage are you going to actually be accruing from these micrometeorites that hit your vehicle. So the thing that I learned is interesting. If you basically, and you can see this has like some damage in it, just poking the hole. As long as you're able to arrest the hole and stop it from spreading, it's not too big. Like there's not very much area that's actually being hit by micrometeorites. It's more like if it hits it and then rips, then you're losing all of that area. So you want to make sure that doesn't happen. So using materials that don't continue to rip once some damage is started is a really big part of that. But yeah, the other thing is you don't want the micrometeorites to hit and damage the center vehicle. So the satellite bus itself, if that gets hit by a micrometeorite, that can take it out. So you're making sure that size isn't too big that it's going to get hit and damaged is also pretty important. But as far as the mirror itself, as long as the damage just goes right through and doesn't make a larger hole, it seems like it's not going to be too much of a problem in the kind of satellite lifetimes that we're looking at. It would take on the order of like 50 or more years to really have too big of an impact on the mirror, which is pretty cool to see. And yeah, some of the mirrors that we actually use in hot air balloon testing, saw a ton of damage. So like they were getting bumped around, they were getting sticks through them, they were getting covered in dust. We really beat the hell out of these things, and all the holes didn't affect the tension. It was still a great mirror, and what we ended up using for the test. So we used the same mirrors for all 7 tests, and yeah, they held up just fine. That was also
awesome.
Cool.
Yeah, do you want to talk about those tests? So maybe take us a step back, talk about the vision of the company, and then how you got started with that demo. That'd be sweet.
Yeah. I guess the vision of the company, it really, like, I've been thinking about energy for my whole life. I built a fusion reactor in high school. I kind of realized that like fusion's probably not the thing that's going to save the world. Just because the sun is so much better at it than we are. It's kind of this like it's very stable system that the sun has, where as soon as something starts going wrong, it just gets fixed. And whenever we do fusion on Earth, we're using confinement methods or something where it's very unstable. So as soon as something starts going wrong, it goes very wrong. We're kind of at the point where we're still solving physics problems, and then we're going to start solving the science problems, and then we're going to start solving engineering problems, and then we're going to figure out how to get banks to back it in order to actually scale it up. It's kind of a very long way away from working. Like solar worked pretty well in the 1950s, and it took until the late 2000s for it to start getting really cheap. So that's a big part of this is like I think we have a long way to go on other energy technologies, and we really need something new. Like we don't have energy figured out, and we really need to find a solution that isn't fossil fuels. Every solution we have, seems to end up burning more fossil fuels than we were originally. And we need to get away from doing that. The other thing that I kind of realized when I was working at SpaceX is we have rockets figured out very, very well. What we don't have figured out is what the rockets are actually launching. So, Elon's whole thing is like, yeah, we're going to go to Mars. It's going to be super awesome. And like, yeah, Mars would be really cool. But like, it's not solving problems here on Earth. Like, what are we doing here on Earth to actually, like, what are we using rockets for here on Earth that's actually solving problems in a real measurable way? I think that's kind of been like a sticking point for a lot of people. And when I was at SpaceX, I definitely felt it like, wow, like these rockets are really awesome, but like, wait, man, we really got to find a better use for them. Didn't have the better use back then, but I think we really found it here, where we can use rockets to launch things into space, get that as cheap as possible, and then use that to actually solve a real problem here. Create energy at night, create energy with rockets, and kind of get that going.
Totally. Yeah, I think people might be surprised to know that most satellites fall into one of two categories. It's either communications or it's imaging. That's like 95% of all the satellites that have ever been launched.
Yeah, or just research. Yeah.
or science. Yes, science is the third category. But that's like the only really like NASA is doing those sorts of things, and they'll send a probe every once in a while to some distant planet. But like all the commercial activity in space is basically just either you're taking pictures of the Earth, and then you're trying to sell that to people that can use it in some way, or you're trying to connect people on Earth via like to the internet. But this is cool. This is like in the third category. This is in the rest of the satellites, and we do need to find more uses for these things. Like, I think it's so maybe the next place to go is just how you got moving. Like, I'm curious to hear. So this sounds like a big engineering challenge, obviously, like trying to create this cool deployable mirror, trying to figure out how to operate it in space. Like, it's a huge problem. So you had to probably break it down into steps and do them one by one and de-risk the company. I think that the way you did that first was by building this hot air balloon test, right? So I'm curious to hear more about that.
Yeah. So I think initially there was a lot of concern that, reflecting sunlight from orbit isn't really going to power solar panels. So what we did is we went out to the desert and we put an 8-foot by 8-foot mirror on the bottom of a hot air balloon and reflected sunlight onto some solar panels really early in the morning and measured the power. And it went from like 58 watts to well over 200. So it is, around 4x the power that we were getting down to these panels. And that's power that would not be there otherwise. Now, obviously, a hot air balloon is a lot lower than a satellite. So it's just kind of like this smaller scale version, but basically everything else is the same. It's a reflector. We use the Mylar mirror, and we were, pulling off the reflection. It's a very moving dynamic system. It's in the real world. It's actually in the sky. So we had to figure out how to aim it in real time, which was a huge challenge. And, we ended up building like 3 separate control systems for that, which was a great learning experience. Some of them are behind me now. And it was just like a great like small scale demonstration of what we're actually going to be doing, with satellites in the future. It was a lot of fun going out to the desert too. There were a lot of times where it was like 2 or 3 days in a row where we didn't sleep, pulling these things together, and actually getting these things operational was pretty cool. So that was a great experience, and it really showed us exactly what we're going to need in order to pull this off from orbit. Kind of the control system that we ended up coming up with is going to be perfect for satellites. It's something that you can kind of do just with a single camera, instead of some kind of other complicated imaging system. And it's not relying on GPS. It's not relying on like internal IMUs or anything like that. We learned very quickly that those do not work nearly as well as you'd expect them to. It's kind of like, oh yeah, we'll just use IMUs and like GPS, and that'll solve the whole problem. We'll know exactly where we are and we'll point right at the thing. It's like, no. That's not how it works. You need much better feedback algorithms and much better information in order to actually pull off a reflection like this. It taught us that, which you can only get that kind of learning by actually going out and testing. Like, it's testing like that. It teaches you all the things that you don't know already. So like you can sit down, you can design something like from start to finish, and you can be like, okay, we know all these things. We're going to design something that's going to solve all of these problems. Then you go out and test it, and you're like, oh, there's this whole new problem that we didn't think about at the beginning. That's the real value of testing, and we definitely found some of those new learnings that we can take to the satellite.
And it's hard to test for space on the ground. I mean, that might sound obvious, but it may not be obvious the exact ways that it's true for people that aren't space people. Like, we have convection down here, so you don't have to worry about thermal things the same way that you do up in space. We have gravity down here, so I don't know. It's hard to test a control algorithm for a satellite. It's going to be operating 0G in 1G. I mean, did you have to do anything cool to figure out how to, how to turn the satellite? Did you test that on the ground before sending up on the hot air balloon?
We didn't for the hot air balloon test. That we actually built up a different prototype. What we did for attitude control was we basically, built a little all of control moment gyros and then stuck them in a hamster ball and put it in a fish tank.
Hell yeah.
Because, it's floating. There's, it's essentially simulating zero gravity. It's able to move around only by what's in here. So that's what we ended up doing for the attitude control system. So this was just like
the
kind
classic NASA designed hamster ball in a fish tank experiment.
Yeah, with 3D printed control moment gyros. Yeah. Another test that we've done is just having like a bunch of fans that are blowing up, simulating solar radiation pressure. Then having a vehicle that can float on those. I can send over a little video of that as well.
That's cool.
Just like building very small prototypes.
Yeah, I remember there was a time at Astronis when we were trying to test because we built a 3U CubeSat. That was the first thing that Astronis built. And when they were testing the gyros, they were trying to figure out the right way to do it. Like, how do you figure out if you can detumble with that when you're on Earth? It's kind of hard. We didn't think of the hamster ball in the fish tank, but we hung it from a string basically. And then we just, and then you just spin it and then see if it can unspin itself.
Go around, see what happens. Yeah. Yeah, it was really surprising how quickly they saturate as well. We developed like a really good intuition for how fast these things saturate and how to desaturate them. It's kind of like you never know until you build something and start playing with it. You can just learn so much from that. And yeah, so we try to do that as much as possible. So me and Tristan are very much of the realm of build first and then figure it out after. So, we throw together prototypes very, very quickly. A lot of what's behind me is just like, I wonder how this works. Like let's just build it and let's just see.
I feel like that's how you've been. I saw your old YouTube channel. I feel like that's how you've been ever since you were in high school. Like literally, you built a fusion reactor in high school.
Yeah, yeah. It's yeah. I don't know. I think it's the best way to learn. It's like you're curious about something, you want to figure out how it works. Like go find one, go take it apart. You're curious how something gets made. Like go build it yourself and really see what all the sticking points are. I think it's more useful than you think to actually just build something yourself. And I don't know, I've always just been curious how absolutely everything works. So, if I can't find a video on how it's made, I'll try to reproduce it myself, in my home shop. And, just after years of doing that, you kind of develop this knowledge, we're able to take on anything. And each project that you do, it builds your confidence. So you want to do more. And yeah, I just think it's a great way to go forward. It's kind of like, it's something that's better to have done in the past. It's like people are always like, oh, it's better to have bought a house in the past. It's like, oh, it's better to have built a bunch of stuff in the past. So I'd always be like, what am I going to wish I did in the past now? And then I'll look to the future. I'll be like, okay, I should build these now so that I'll be happy when I look back on it. And it's just kind of like that thinking that yeah, it adds up over time. It has a big impact.
Totally. Talk about how you decided on this architecture for beaming energy from space versus choosing other things. Like there are other models. People have tried people have talked about the mirrors that shine light onto something in the satellite and you just beam it down via laser or microwave or something. Why'd you choose just to reflect light as opposed to beam down lasers?
Yeah, I actually got here in a completely different way. I was not thinking about space solar at all. I was watching a video on the problem with solar power in Africa, and below here, in the video, it was like, you put a little square in the Sahara Desert and it can power the whole Earth, right? Like everybody's seen that. But this video was interesting because it said Europe was going to spend $42 billion to build a bunch of power lines to bring solar power from the Sahara Desert to Europe. And, they're going to power Germany because they were like, the Sahara Desert gets 3 times more sunlight than you get in Germany. So, it makes sense to do this, and the economics actually work out. And I was like, holy crap, that's completely crazy. $40 billion. Like, I bet there's a better way to do it than spending $40 billion on a bunch of copper cables. So I started looking into actually turning the sunlight into, beams of sunlight and then reflecting it off of mirrors to get around the curvature of the Earth, and then converting it that way. Because the thinking was, light moving in a vacuum is the most efficient way to transport things in the solar system. Like light from 13 billion years ago still makes it to us, and we're able to see it when we look really deep into the stars. And a little bit of stainless steel around the edge of a vacuum tube is more efficient at scale than, a bunch of copper that's carrying high voltage. At least that's what I was calculating out. And, it was kind of crazy, but, it got me thinking about this problem. And I actually started building up some hardware for it. This is like a giant mirror. That was one of the things that would focus it in and bring it into a beam. And there's some problems with that. I was, I was a little bit naive, just kind of doing high level calculations, looking into things. But, what I ended up learning when I started to talk to people about it is, why are you doing this? Photovoltaic solar is just going to absolutely crush you. You can buy solar panels, it's less than $1 a watt. It's like 20 cents per watt now. Where it's gone down 34x since the 1990s. It's just so cheap. And there's 2,000x more solar farms out there today than there were, just 30 years ago. So it's just absolutely ripping. And the big thing is banks back solar farms, and they're very comfortable with it. And banks will not back your idea for a very long time. So long that you're never going to beat solar, and it's just going to continue to beat you. So I was like, oh man, this is a very big thing in my brain. And another really big thing in my brain then was, SpaceX Starship and how that vehicle is super cool. And, I kind of made the choice to go and work at a bunch of startups, to build my skills instead of working on Starship. Because I was like, Starship's very cool, but I feel like there's something else to be working on. So every time I saw Starship working really well, I was like, oh man, maybe I could have gone and worked on that thing. So I had these kind of 2 very negative things where I was like, oh man, photovoltaic is just winning everywhere. They're so good. Man, that's crazy. And then also Starship was also working out very well. And I feel it's this kind of thing where negatives in your brain are always stronger than positives. Because humans are designed to avoid things that are dangerous. But we're not designed to just hang out. It's just, this kind of innate human thing in our brain chemistry. So I had these 2 negatives, and then one day I was just on a run and I was like, wait, what if these negatives were actually positives? And I could use them together. And I was like, what if I used cheap launch to launch things into space that could make photovoltaic solar better? that would just be a mirror. So that like I could actually put reflectors in space, shine sunlight onto the solar farms after dark, solve the biggest problem with solar, which is actually not that it's cheap or, not that you have to bring the power lines places. It's that the sun goes down every single night and all the solar farms around the world stop producing electricity. It's like a coal power plant that can't buy coal after 7 p.m. For every solar farm, no matter how big of a solar farm you build, it stops working at night. So yeah, I just kind of combined this thinking together, and I was like, wait, I could use the cheap rockets to launch a bunch of mirrors into space and shine sunlight onto solar farms. And the biggest thing about that was instead of going from here to here on Earth, you could just go from right above the atmosphere to right below the atmosphere. So this is kind of just like a huge breakthrough that I just had when I was on a run, and I was like, oh yeah, this might make a lot of sense. And the more I looked into it, the more math I did, the more it kind of started coming together, and it was like, oh, this is actually competitive with every other energy technology out there. Even with like, rockets that are working right now, we can make this cheaper than batteries. And it's just like, holy crap, like this is amazing. This is an amazing new energy technology. Why is nobody looking into this? And then after that, I started looking into, power beaming and stuff. Because people have thought about this before. NASA thought about it in the 1970s. Oberth wrote a paper about it in 1929. And then, there's been a couple companies along the way that have been thinking about this. And, the traditional approach right now for like large institutions, and Caltech just launched a vehicle is doing this, is you have solar panels in space, you convert it into microwaves, and then you beam the microwaves to the ground to a bunch of antennas in the ground. Now, there's a couple problems with doing that. The first one is the antennas are really expensive. So you need like, an 80 dBi antenna or something like that, which is like, the 500 meter diameter aperture, like Arecibo, like these radio communication, like these things that listen to aliens and stuff. Like the very big antennas are kind of like on the scale that you need for this. And Ronald Berger did a study on the European Space Agency's design, and they said it was going to be $9 billion just for the steel alone for one of these antenna farms on the ground. That's just for one farm, and you kind of need a lot in order for the idea to start working out. Because the satellite's always moving, so you need to like, always be sending it to a new place. So it's, it's kind of crazy. And then you actually do the calculation, and it turns out that just the solar panels are similar to our entire cost. So, solar is a certain dollars per watt. A solar panel going into space is even more expensive per watt. And, a piece of Mylar going into space is very cheap, and it's very light. So it doesn't, it's super easy to get out there. So it turns out like just the solar panels are basically more expensive than our entire system. And then that's not including the thing that you're using to transmit to the ground, whether it's a microwave antenna or a laser. Also, it turns out usually that thing gets very warm, so you need a giant radiator, which can be as big as the solar panels. And then you need all these ground stations, which we don't have to build because people have already built solar farms all around the world, and they work really, really well, and they pay themselves off. And everybody's happy with that kind of investment, and they're just growing extremely rapidly. It's the fastest growing new energy source. Like most new energy projects are solar projects. And they got extremely cheap over the last decade when a bunch of other energy technologies have gotten more expensive. So kind of looking into all of these things, it's like, wow, why is nobody working on this? And it's, people have been working on this. The Russians launched the vehicle in the 1990s. That was, basically doing the same thing. It's just, there weren't a bunch of solar farms built around back then. So there weren't any customers to send the power to. And, people have looked into this in the 1970s, and, it just looked very expensive back then because, the cost of launch was ridiculously expensive back then, and, only NASA did it. But, nowadays there's commercial space flight. And that really makes this whole thing work is, there's these vehicles that are launching up, and, I don't have to worry about them. I don't have to worry about building a rocket. I don't have to run a business like SpaceX, which is great because, the rocket businesses are really hard businesses. Rockets blow up. It's actually kind of funny. Like satellites were able to make a lot of money before SpaceX even existed. Like they were able to launch on like $400 million ULA launches or something like that because the economics make so much sense. But the actual rocket itself is a very difficult business to run. I'm very glad we don't have to do that. I'm glad that there's people making great rockets, and that we can just purchase them and use them and get our stuff into space. Yeah.
I think it's so interesting. It's like both a super cutting edge technology that is, launching this massive object into space, like something that people haven't seen before. But then at the end of the day, it's just connecting to like a solar farm, or which I have on the roof of my house. Like it could literally shine light onto my house and it would produce energy for me. I think it's a cool dichotomy, or it's a cool mashup of those two, like old and new. I think one question that I have is, like how much more solar are you getting than normal farm? Is it like multiple hours? Do you think about it in hours? Do you think about it in watts? Like how do you think about how much more productive you're making the average solar farm that would be a customer of yours?
Yeah, we have a lot of flexibility on if we want more power or more hours. We're doing a little bit of a blend right now. So it's like, 2 hours at night, 2 hours in the morning, and then, a couple hundred watts per square meter. So at the point where it's like, 200 watts per square meter for 2 hours, it's like 20 or so percent more energy for the solar farms that are out there. But theoretically, you can quadruple the output of an existing solar panel. This is thing that I like to say a lot, where it's the sun only shines 25% of the time on average in the US. So you put a solar panel outside, you put a 100-watt solar panel outside, it only makes 25 watts typically. We can bring that up to realistically like 80 watts, which is pretty cool.
Because you're reflecting more sunlight. You're getting double sun, basically. If you were a perfect reflector and there was no atmospheric loss, you would have like double sun going for that square footage, right?
You just add enough satellites that you get that power to the ground. Yeah. So you can just
But you're like overloading a normal solar panel, basically. Like you're letting it see more than it would normally see just from the sun coming down on it.
Yeah, and I think we do have to be a little careful about overloading, because we're not bringing more light down than the sun. Like it's not brighter than the sun. It's just for longer. So usually, the sun is up in the day and then it's gone at night. We just keep it going later in the night. So we're not like making double power sunlight. We're just like keeping it going for a lot longer. At that times when it would normally be off, and those are the most useful times of day too. Like at night, you kind of get like the peak demand thing on the duck curve. We should definitely show a picture of the duck curve here. In California, where there's an awful lot of solar on the grid already, you get like the demand curve, and then you subtract solar's output from that, and you get this. And then when you do that, you get this huge spike in demand late at night as the sun is going down, and you get this other demand, right before the sun rises. When people are waking up, they're doing things, but the sun isn't providing a lot of solar electricity. We come in right at those hours and provide that extra power. So it's not only like adding more power, but it's adding power exactly when solar farms need it most, and exactly when energy consumers need that power most. So yeah, that's pretty cool. And the way we do it is just with like a sun-synchronous polar orbit. So it's like a fairly standard orbit. Usually you use this orbit to take a picture of the Earth when there's no shadows on the ground. We just do that 90 degrees offset. And we stay in this orbit. We're locked to the sun all the time. The cool thing about that is the satellites are always in the sun. We're never competing with the sun during the day, and we're not shaded by the Earth at night. So that's a great place to put your satellites, and you get an awful lot of output out of your satellites as well. Because the thing is, when you launch these satellites, you want them to make money back. When you do the math out, like kind of at scale, like I like talking about the numbers when we're kind of at maximum scale. On the economic side. So, we expect to be able to make these satellites for like around $100,000. If you're launching that on Falcon 9 ride shares, it would cost like $150,000 or so per vehicle. But if you kind of do the economics out with Starship's launch costs, you're down in that like $30,000 per vehicle range, which is really crazy. And then with each of those satellites, you're basically able to make like $175,000 per year, over the lifetime of the vehicle. At first we're going to be like 10-year life vehicles, and then in the end we expect to want to get up to like 20-year lifespan vehicles. We don't have the same thing where version 2 is going to be a ton better than version 1. These are mirrors. They're going to be like 90% reflective. They're pretty good. Like version 1 is going to be very, very good. Version 2 is going to be very slightly better. We're not going to find aluminum 5.0 and make this a lot better. It's already really good. We can make the vehicles last a long time. That's great for energy because we have this very fixed revenue that we get over a long time. That's pretty cool. And I think like the scale that I'm most excited about is when you have like 250,000 of those satellites. You're talking like $22 billion in CapEx, right? You're serving all the solar farms around the world, so you're able to use the satellites like 20% of the time or so. And you make $70 billion a year for 20 years, so you end up netting like $1.4 trillion. So that's kind of the economics at full scale, right? It's like,
oh my god,
yeah,
those numbers are like
I can't even. Like
those numbers mean nothing to me. Like you said all those numbers, and I just don't even know. It's like, oh my god, like how many zeros are in each of those? It's crazy.
Yeah, yeah, it's very large, and it's pretty impressive too, because it's like that's revenue that you're going to be getting as well. It's not like an oil rig. Like you spend $2 billion building an offshore oil rig, and you're not really sure how big that oil reserve is until you actually tap it and get a drill down there. With this, we know how much sunlight's out here. Like, it's all just missing the Earth. It's actually crazy. Like, in most of the solar system, there is sunlight. Like, there's only a very few places in the solar system that are shaded. Like, right behind the Earth, like right behind all the planets, like there's a tiny bit of shade. That's a tiny, tiny percentage of the solar system. So we just need to get things like out in places in the solar system where it's always sunny forever, never shaded. And that's kind of thing.
The sun's angle from Earth is like half of a degree in the sky or something. So it's like, yeah, so that gives you a set. Then multiply that. It's not even just a one circle either. It's like the it's obviously multi-dimensional. It's not one single dimension. So that's,
So there's a cool
you're wasting almost all the energy. We are currently.
No, it's crazy. So the sunlight that hits the Earth in 1 hour is enough to power all of humanity for an entire year. Right? I think people have heard that, but it's also all of the sunlight that doesn't hit the Earth. It's 2.1 quadrillion times more than hit the surface of the Earth, because we're like a tiny little sliver. Like, the sun is a half a degree in the sky, but the Earth from the sun is way smaller than that. I did it was like 10 to the minus, I actually forget, but it ends up being 2.1 quadrillion times when you do that for the whole
2.1 quadrillion. Again, I have no idea how many zeros are in the number, but it sounds big. Very cool. So talk about the scale of the constellation you need to start. So like, if you have one satellite up there that is one reflector, you can, and normally that sun-synchronous orbit goes around every 90 minutes or so, depending on your altitude. But I assume, what altitude are you at, actually?
Oh, we're at a 600-kilometer orbit.
600-kilometer orbit. So yeah, that's like a fairly standard low Earth orbit altitude. You're orbiting roughly every 90 minutes. And so what that means is that any given spot on the ground, any given solar farm will only see you for like 2 or 3 minutes per rotation around the Earth. So how many satellites do you need in your cool sun-synchronous orbit to be able to serve a customer for an appreciable amount of time?
Yeah, if you want to fill out an entire ring, you need 57 satellites. Because you basically just have one pick up where the last one left off. That guarantees service anywhere on Earth for about a half an hour. Slightly less than a half an hour, but about a half an hour. So you do this ring.
Half an hour on either side of the day. So 15 minutes in the night, 15 minutes in the morning.
Yep.
Okay.
Yeah, so that works quite well in the sun-synchronous polar orbit. But and that serves any solar farm on Earth for that time. So like, a solar farm in the U.S., like on the East Coast goes through it, and then 3 hours later, a solar farm on the West Coast goes through it. So like everybody goes through that ring. But if you want to serve just a single location and you want to get as much power as possible down to that, you can do another like kind of special helix orbit. So like, in the early days when we were just serving a small number of solar farms, they're all kind of localized together. Like say Southern California or something like that, there's a lot of solar farms close together. We can do kind of a helix orbit, and with that you only need about 20 satellites to have the same service duration. So you can get like a little bit better gains when you're optimizing for just a couple single locations instead of the whole Earth. So we'll be doing that a little bit early on. The other thing that we can do is we can serve other customers early on. So serving energy customers is kind of like the end state. That makes sense when you're launching like, full Falcon Heavies full of vehicles, and you're getting a lot of power to the ground. Like, the economics start working really well when you sort of do that. When you spend like, around $150 million or so, the energy case makes a lot of sense. When you're launching kind of that first full Falcon Heavy full of vehicles. But even before that, this can make sense because it's 13,000 times easier to compete with streetlights than it is to compete with the sun. So streetlights are actually a lot less bright than the sun than you realize. Like, the human eye is so dynamic. They look about the same, but they're way, way dimmer. So we can actually use like smaller constellations of just single vehicles to light up cities at night. So in places where they're industrializing, where you don't currently have streetlights built, you can just go onto our website, figure out where you want the thing to point. We can send down like a 5-kilometer spot of light that's just as bright as streetlights. So that works really well if you don't want to put in streetlights, if you don't want to have the light bulbs, you don't want to have all the maintenance, you don't want to have the electricity. If we're almost as cheap as just the electricity, all the other stuff is extra. So we're actually a lot cheaper than other options there. And you can also use that for just like very flexible lighting. So if you're doing construction in the Yukon, and it's dark 22 hours out of the day, and you're filling up diesel generators to run lights to light everything up. You're like, we make a lot of sense for those kind of applications.
Wow,
just lighting up the region. So that's one of the earlier things. We make a little bit more margin on that. Obviously, it's a smaller market than energy. Energy is just like this gargantuan market that we can scale into forever. But in the early days, that is a big portion of the revenue of the smaller constellations.
So what is the order, or what's the quantity that you want to launch these things in? Like first launch, 2-ish satellites, I think you said when we talked earlier. In the future, you want to launch bigger batches, presumably. And then eventually you have to get up to 57 is the goal to actually do the energy case. So what's your walk to get there? Like, how are you thinking about the stages?
Yeah, so I mean, right now we're raising our seed round to launch 2 satellites. So 2 of those 12U CubeSats with the 10 meter by 10 meter reflectors. After that, we want to launch 60 vehicles. So we're going to raise the Series A, launch 60 satellites, and that's kind of the full constellation. We can serve energy customers, we can serve lighting customers, we can serve a couple of other customers that we can talk about later. And yeah, that basically just like gets the ball rolling. We know the constellation works. We're going to use that even the first 2 satellites that we launch. We're going to do a world tour, go to solar farms everywhere. Have the satellite flying by in the sky, click spacebar, boom, here comes the power. You can see it on a gauge and be like, oh yeah, we're getting some power through this thing. Like, you launch more of these things, we're going to be getting a lot more money. The scaling from there is also really simple. So like, if you want twice the power, 2 satellites combined together. If you want twice the duration, add 2 more behind them. And it's very simple scaling after you have that one vehicle. So even after we have that one vehicle, we know exactly how much power we're going to get with more vehicles. And then, yeah, we raise more money, launch 60 of them. That gets a lot more power to the ground. Be like, yeah, look, everything is great. Like we're getting a reasonable amount of power to our customers. And that's going to allow us to book a lot more customers. The cool thing that happens then is we can go to banks, or we can go to, we can basically take that, do the economic analysis, and then go to other investors or banks and basically take out debt in order to finance kind of the later rounds of this. So around that stage, you really want to get to the point where you can raise debt and pay back loans. Like that's the thing that isn't really present in space right now. A lot of times it doesn't make sense, but it does make sense for things that are a lot more trustable, and it definitely makes sense for energy. Like if you're going to build a solar farm at your house or on your farm, like a giant solar farm, you're going to take out debt for that because you're going to get paid back on that solar farm. Especially these days, banks are very comfortable backing solar farm bets. So we want to get to the point where we can do that as well. And I think like we have this kind of unique opportunity where once we have all these customers around the world, once we're serving them sunlight at night, they know how much power they're getting. We have dozens of them. We know exactly who they are. We know that we can put more solar farms up there and, get sunlight in places that it's not shining. It's going to be very easy to make the argument that this makes sense to keep scaling up. And it's going to be very easy to make the argument that we can pay back loans when we have a good track record of performing exactly as expected. So there's this kind of like credit worthiness that we're going to be building up over time, which is going to allow us to scale so much more down the road. You don't fund a $2 billion offshore oil rig with all equity. You fund it with a lot of debt because that reserve is going to pay back, and that people are going to be buying that oil. We're kind of like it's this whole thing, and I know you mentioned this in one of your videos. It's like there's no market risk or very minimal market risk. Like we're selling electricity, we know what the cost of that is. It's a commodity. As long as you're cheaper than the other options, you're going to have a lot of customers. And we're really just selling electricity to keep the lights on at a time when it's most valuable. And as soon as the cost makes sense and it's cheap, and we can continue to support that, and if it all works out on paper, we're going to be able to build a lot of these, and we're going to be able to take out debt in order to do that, and that's just going to be amazing. And we're going to be able to launch a ton of these things.
I mean, it seems there's no reason why a solar farm would say no to this. I literally can't think of a reason why they would say no to more sunlight.
Yeah, I mean,
so
it's the reason you build a solar farm in this valley instead of this valley, because you're going to get slightly more sunlight here. People don't build solar farms in Alaska because there's no sun up there. It's kind of the same thing with this. You build a solar farm where the sun is, but now you're actually able to bring the sun to where the solar farm is. I kind of see it like irrigation. I kind of like explaining it like that. Like right now we put solar farms out there and we just kind of wait for it to rain on the solar farm. We just kind of like sit around like, oh man, I hope it's sunny tomorrow. Like, oh man, it'd be great if it was sunny tomorrow. We're giving these owners the option to be like, it's going to be sunny tomorrow. I'm going to pay for it. Like we need it to be sunny tomorrow in order to pay back our bank. Cool. So they can cut us a check. We can send them some sunlight, and they're going to be able to sell it for more money than they buy the sunlight for. And they're going to make some money on it. So they can confidently say it's going to be sunny tomorrow. And actually it's going to be sunny tonight. So at times when it's previously like not available.
It's going to be sunny tonight. That's a sick motto for you guys. I love that.
Sunlight after dark.
Sunlight after dark. Hell yeah. Okay, we still haven't talked about what I think is maybe the coolest piece of technology, which is the solar sailing. We haven't talked about solar sailing and what it is. So tell us what it is and why you're using it, and how it works.
Yeah, so with these vehicles that have gigantic reflectors for providing energy, we can also use them to reflect sunlight and get a little bit of a push from it. So photons don't have mass, but they do have momentum. If you look at, kind of Einstein's like longer form of E equals mc squared with the momentum included, they have momentum. So we can actually use that to get a little bit of a push to keep our satellites in the air. And this is not something new. The Japanese JAXA mission went by Venus in the 2010s, and that was super cool. It had like little LCD screens to actually steer it as well. To change the amount of reflection that you're getting from the sunlight. And they flew by Venus with it. They got a little bit of delta V from it. And there's been a bunch of NASA missions, getting a little bit of extra delta V from solar sailing. So we can do the same thing. This has always been a component of our energy solution. Like, if you want to keep something in the air for a long time, you don't want to have to burn propellant. You want to do something else if possible. Propellant on satellites is kind of what's limiting them. It's usually why you have a short lifespan in low Earth orbit, because you have to fight atmospheric drag the entire time. And, burning fuel to fight atmospheric drag really takes a lot out of your satellite. And, it's hard to bring enough fuel because it's super expensive to launch that on a rocket. It's also this constant thing that you have to fight, and you cannot refuel satellites, at least not right now. There's some people working on that, but it's very hard to refuel satellites. So like you launch this thing up, it's just slowly running out, and bringing more is very expensive. So typically you just are like, okay, we'll just leave the vehicle up there for a very short amount of time. We don't want to do that. So we want to actually use the satellites to solar sail to give us a little bit of a boost so we don't have to burn propellant. So what we can do is we can just aim in the right way so that when the sunlight reflects off, that force vector lines up with our velocity vector and we get a little bit of a push. And when you do the calculation out, you can sustain in orbit. It should be above like 530 kilometers, you should be good after that. But because the atmosphere, the sunlight hits it, it grows a little bit. There's some variability there. You want to leave some margin. So we're going to be leaving some margin. But basically, we can use solar radiation pressure to push our vehicle along and maintain our orbit instead of bringing propellant. Now, this is obviously great for our energy case, because we can launch satellites that don't have rocket engines, that don't have fuel, that just have, electrically actuated motors to steer around. But it's also potentially a very great business early on as well, because what we can do is we can bring people on with us. And instead of just serving energy customers and making money, over a number of years, we can make money right off the bat by bringing sensor packages around for people. And this kind of doesn't stop with low Earth orbit as well. Like we started looking into it, and we should be able to get a Falcon 9 rideshare. It launches us into low Earth orbit, just like a normal CubeSat, but then, deploy our solar sail and we start solar sailing around the Earth, and we can actually bring that payload to other places. So we can bring a payload from the Earth to the Moon in a little over a year, from the Earth to Mars, and also a little over a year. And we can go to like Saturn in like 8 years. So we can kind of fly anywhere on Earth, as long as the electronics last long enough. You do need radiation hard electronics to go this far. And it does take a while, and we can't bring a ton of mass, but we can bring some mass. And this is kind of an option that previously you'd have to make yourself. You'd have to, have an insanely custom satellite, gigantic prop tanks, gigantic rocket engines. But now it's just one vehicle, with a little solar sail. It's the same vehicle. You can go to all these different destinations. You don't have to change the shape of the vehicle in order to go to a different destination. So originally we were a little bit worried that this would be, kind of a super different vehicle. But the more we look into it, the more parts commonality it has. Like it's basically the same satellite that we have for our energy use case, which is really cool to see. So, we kind of just make this one vehicle, and initially, it can serve like the kind of solar sailing customers who can pay money up front. And then obviously, we also serve the lighting customers, on the ones that stay around the Earth. And then we can also serve the energy customers. So yeah, right now it's like, we want to launch 2 vehicles. We want one of them to kind of go on some really cool mission, off into the solar system. And we want the other one to stay here on Earth and do demonstrations here. So that's kind of what we're converging on now. And it's this one vehicle that can do all these different things. Yeah. One thing that's always bothered me about satellites is they're always built for one specific use case, and you can't do anything else with it. You build a satellite that's going to go to the Moon. You're not going to use that in low Earth orbit. Like you build a satellite for an asteroid. It has exactly enough fuel to get to that asteroid, and not really for anything else. So you never change your mind when you're going to a destination. Like that would be completely impossible, completely ridiculous. And this has always kind of bothered me. Like that's not like the most useful vehicle. Like building one thing for each use case is not efficient. Like what if you could build one thing for all of it? So I've always been kind of obsessed with this idea of like, the drill for space, where you just build one tool that's really, really good and you can use it for anything. You can use it to drill holes, you can use it to put screws into wood. You can do kind of anything with this one very useful thing. And if you just focus on making the tool really good, you can use it for everything. And I think solar sailing is kind of the way to do that. Like you build one really good solar sailing vehicle that gets a lot of performance out of the sunlight that hits it, and you're able to get to any destination very, very quickly. And then you just build, if you want to bring heavier stuff, you just build like a larger screw gun. Like, if you want to drill something with a bigger drill bit, you build a bigger one. But it's basically like this kind of like tool, this useful thing. It's like this one unit that is like kind of the perfect form of the thing that you're trying to do. And I see solar sailing vehicles as that for space. It's like, it solves the fuel problem. You don't need to bring different size prop tanks. You don't need to bring different amounts of fuel. You don't need to sit there worrying like if you have enough propellant to make a certain maneuver. Like, it's this huge issue. And like we kind of get away from it with solar sailing. And I think it's only going to improve. And, solar sailing has been proposed, to do a flyby of the sun and then shoot off to other star systems and stuff like that. You can do some really amazing things with solar sailing vehicles as we make them lighter and larger. And nobody's really commercialized this yet. I think it's always been something that NASA has done. But I think it's just starting and it's kind of ripe for commercialization. I think the thing it's always kind of been missing is a really big market. It's like, solar sailing is really cool, but the market's too small. I think because we're making this one vehicle that we can use for solar sailing, that we can also use for energy, we kind of have this great entry point to this humongous market. So we make this one vehicle, we use it to serve energy customers, we use it to serve our solar sailing customers, and then, we just kind of grow it. And as the solar sailing market kind of saturates out, we can still justify having a really large team working on this problem because we're able to serve this energy market. And that energy market is just massive. We really are prototyping a new form of energy here. Like, it's like building a new nuclear reactor or something like that. And even just one satellite is going to show us exactly how that performs. So yeah, that just gets me really excited. It's like there's this new form of energy that nobody's really thinking about enough, that we're going to be able to make work. And it's like, we build one satellite, it kind of like, unlock satellites so they're able to fly anywhere. We're able to bring people anywhere. I've always had this dream of beating NASA to Europa, and like maybe this is the way to do that. And like, yeah, and then you just keep building them better and better, and then it turns out you can have this gigantic market. You can actually use them to solve the climate crisis potentially. Like we build enough of them, we don't need to burn as many fossil fuels. That's how we see it.
Very cool. I'm curious. So the reason why I think I am personally like, I don't know how useful like solar sailing is for all these applications is it's such a tiny amount of force. Like actually, I looked it up before this just because I was curious, and 1 square meter sees 9 micronewtons of force.
Yeah, it's 10 to the minus 6. Yeah.
Yeah, it's like I was like, what? I had to do some Googling to figure out what is actually that small. And it turns out that it's roughly equivalent to a single red blood cell dropping onto your hand at Earth gravity at 1G. So it's like very, very, very small amounts of force that are being imparted by those photons from the sun. So can you actually like carry an appreciable payload? Like how big could the payload be with something that's your size, like a 10 by 10 meter solar like light sail?
Yeah, you can bring just like a kilogram or two, basically. Not very much. Yeah, a lot of satellites are like 300 kilograms or something like that. There are a large number of smaller CubeSats, and that's our market. Like just like the 1U CubeSats, the 2U CubeSats. Those super super small payloads, or even less than a U. And the other thing is, yeah, because it's such a small force, it takes a long time for it to add up to a lot of delta V. So that's why it takes so long. That's why some of these missions are like a year or more years. So it's like that very tiny force, but it is a constant force that keeps pushing, and over a very long time, it adds up to be quite a lot. But
it doesn't. You could blast it with a laser. That would make it go faster.
Yeah, you can. A few people have been looking into blasting it with a huge laser. Yeah, I don't think we're going to be going quite that crazy. But it is definitely something to look into. I think one cool thing is the orbit that we're in is actually really good for solar sailing. Because we're in this orbit where we're always in the sun, we can always kind of get this little push from solar radiation pressure, and we can always use that to counter atmospheric drag. So that's pretty great. So instead, a lot of times like solar sailing vehicles have been kind of going this way, where you only get like a little push when you're on this side, and you have to rotate this way to go through this way. When you're actually in this orbit, you can get a push, kind of all the time. And it pushes you this way a little bit. That ends up just working out to being like a little bit of extra potential energy. But you do get this kind of like constant push like around the entire circle.
So here's the thing that conceptually doesn't make sense to me about that. It sounds like there's two different things that you want to do for pointing. Like there's one piece of pointing that is, let's maintain our altitude pointing. Basically, let's counteract atmospheric drag. Let's keep our altitude high. Let's make sure we don't fall into the atmosphere. And then there's another piece of pointing, which is you want to point to a specific place on the ground for a solar panel, for a solar farm. So do you have to like cycle the satellite in between maintain altitude pointing and point at solar farm pointing, or those two things end up being the same?
You do cycle between them. So, we spend a lot of time over the Pacific Ocean or the Atlantic Ocean or something like that. So in those times, you're like, full-blown solar sail mode. We can do a little bit of pointing, like when we're flying over a specific solar farm, we can kind of like bias a little bit. So we get like a little bit of extra solar sailing. Like it's not ideal for solar sailing, but it's nearly ideal for the solar farm. So we can get that little bit of a push most of the time.
Okay.
But yeah, we do most of the time in our orbit. Actually, we're not over solar farms. Like it's only like 10 to 20% of the time you're over a solar farm that you could even serve. So the rest of the time you're just able to.
You're
focus
just maintaining
on
altitude.
sailing.
Yeah, that makes sense.
Maintaining altitude.
One piece of this, obviously, I mean, how do you actually do that pointing? Like, I think you have most people will use something like a reaction wheel, which is just like a flywheel that takes momentum, or like, what's the simplest way to describe a reaction wheel? It's like a thing that you can turn, you can spin up, and then it imparts rotational momentum in the other direction of where you're spinning it up.
So the analogy I like is like dirt bikers when they speed up or slow down their back wheel. In the air, and they can like change, like if they go off a jump and they can like change their angle of attack by speeding up or slowing down their back wheel. That's like the reaction wheel analogy I like. Yeah, control moment gyros are super weird because they're more like you have your front wheel of your bike going and you turn it like this, and it ends up like moving the bike forward and backward. So nobody's ever used to control moment gyros. We've made a few models. I think this is like a simple one to look at. And I have a video I can send you of this like hanging from a string, and you basically spin this up, rotate it like this, and then the whole thing tries to spin very quickly in this direction.
Yeah.
So it's kind of not intuitive, but it's really just like adding up. You have this angular momentum that's going in this direction, and when you rotate the angular momentum vector, you get another vector that's coming off in another direction, like per the right hand rule. And yeah, these are really great because they get more you get more torque from the same mass. Which is fantastic for a satellite when you're trying to get a lot of torque. We want to move our satellites very, very quickly between solar farms, so we want that high torque. So we're able to really crank this thing around. A lot of satellites are like pretty anemic in the way that they move around. They're super slow. Like we don't have 5 minutes to make this rotation. We want to do it in like 10 or 20 seconds. So we really need this high torque. And yeah, what you're able to do is instead of just having the thing speed up and slow down, you're rotating the entire wheel around. And it's staying at its maximum RPMs the whole time. So you're getting a lot more bang for your buck with control moment gyros.
Interesting. So do you have to desaturate them in the same way that you have to desaturate like a normal reaction wheel?
Yep. Yeah, you do. Because when you rotate it, like you run out of rotation at a certain point, and you're not able to put any more energy back into it. So the thing that we're able to do is we're able to desaturate our CMGs by using either atmospheric drag or solar radiation pressure. We can do that. Little prototype. You can basically
there we go.
little flaps on the corners. So yeah, if this is your solar sail vehicle, you just have these little things on the ends, and you can basically rotate it like this to have no drag. You slip right through. You rotate it like this, and you get a little bit of a pushback as they're flying through. And if you have 4 of these, you're able to create any direction that you need. You can also do it by changing the center of mass of your vehicle. So like, have these servos, so you can change where the center of mass is. Turns out like this is a little bit more annoying to build and use these little flaps on the corners. Pretty confident that we're going to end up going with these. But yeah, there's a couple of options to desaturate your CMGs. Changing the center of mass changes where the center of pressure is going to be. So when you have more pressure on one side of your center of mass, you get a rotation from that. So you can use that to desaturate your CMGs, but you still can't desaturate roll by changing your center of mass.
Sure.
So that's where these flaps really come in handy is to change your roll.
Very cool. Yeah, I think just to like take a step back and explain what we're talking about. Like basically, when you're spinning up this thing, eventually you get to the point where you just can't get that momentum anymore. You have completely maxed out the ability for you to go in a particular direction. So what you need to do is you need to have some other way, something that is not that wheel, that is moving you in a direction that allows you to sort of turn down the amount that you're spinning the main thing.
And usually satellites use rocket engines for this.
Right.
Usually use thrusters, but if you do that, you're eventually going to use up all your fuel. And then that's where a lot of station keeping losses come from. Is you've moved this thing too far. and you want to be able to move it back so you can keep using it. And instead of burning thrusters for doing that, we're able to use this other system, which is using a very small force. And it's like the force that acts on that is over, many days in a row. And this thing moves very quickly, like within a couple of seconds. So there's kind of like the slow thing to desaturate and the very fast thing to do the rapid motion, which is like, a pretty cool configuration to actually have in the vehicle. Yeah. And we're pretty happy about that.
That's cool. It's kind of the opposite, actually, of what a reaction wheel normally is. Because normally they don't move that fast, and then you are desaturating them quite quickly as you're like blasting with your thrusters.
Yeah, exactly.
When you're designing the constellation, figuring out, where to position all the satellites within the orbit, trying to figure out how many of them you need, all that kind of stuff, I imagine you had to do a ton of simulation. So can you just talk about how you did that and the joys of Monte Carlo?
Yeah. Yeah, the initial problem statement is how much power can you get to the ground per satellite? Because you kind of want to maximize the power delivered per satellite, right? So I started with a data set of 30,000 solar farms all around the world, how big they are, and their actual geographic location. And then I basically was able to plug that into a Monte Carlo simulation where I would pick satellite locations, like potential satellite locations within a distribution. And then I would figure out, okay, if I'm going to serve that solar farm, what angle am I going to have to be pointed at? When I am at that angle, how much light am I losing coming through the atmosphere? How much light am I losing at the solar farm itself, either because of cosine losses where the light isn't quite aligned with the panel, or if there's not panels there. And I can basically add up all these losses, add up the amount the atmosphere absorbs, add up if there's clouds in the way, there's a probability that there's a cloud in the way. So you have to add that up over time as well. Also, like when the mirror is at an angle, it's like kind of it's like a little bit smaller in the sky. And this one was really fun to figure out. So if a mirror is like this, it's very large, but when it goes over an angle, now it's much smaller in this dimension. So, if the camera is the sunlight, there's a lot less sunlight hitting this now. So you're going to get less power to the ground. So you also need to optimize for where you're pointing, and how you're pointing there, because you're going to get less mirror area. So yeah, it includes all of that, and it basically adds up all those numbers for each satellite location. And then, you just do that for billions of satellite locations around the Earth, at all the different angles, essentially throughout the year. And then you're able to add up the amount of sunlight that gets to the ground per satellite. And we actually calculated out in the amount of sunlight that gets to the ground per solar farm customer per square meter of area. And then when we do it like that, we're able to calculate it with different size vehicles. So you can optimize the scale of the vehicles on its own. And you can also optimize different curves of customer saturation. So initially you're not going to have as many customers excited to buy, a couple minutes of sunlight that's not very bright. But later down the line, you're going to have a lot of people who are very interested in buying a lot of sunlight. At the kind of point where we're, a couple hundred watts per square meter for quite a while. We expect a lot more people to be buying sunlight then. So, you can kind of do all this analysis with this input that we get from the Monte Carlo simulation. And we get a couple of interesting things out of that. So the first thing that's interesting is just utilization. So you launch the satellite into space, it's flying over the Earth, picture us as a satellite. How often is there a solar farm under you that you can serve? That's a pretty big question. And, the Monte Carlo simulation, it just spits out a result for that. With all the solar farms that are out there, it's 13% of the time you're over a solar farm that you can just serve. And then, you assume a customer adoption curve, and it's okay, it's about 6% of the ones that are large that are likely to buy it. So you can get these numbers pretty easily from that. You can also just get the number of how many megawatts do you get to the ground per hour per customer. You can get all these interesting numbers out of this simulation, which is really useful. And yeah, so I don't know, I had the idea to do this pretty early on. I was pretty excited about it because it's a lot easier to do a Monte Carlo simulation of all the satellite positions than it is to simulate orbits. And when you do that, you have this time component, so you end up having to iterate the thing over time, and the simulation would take months to solve. But if you do it as a Monte Carlo simulation, you don't have to have all of that. All time is kind of the same. So you're able to make the sim work a lot faster. And we had somebody who's an orbital analysis expert do this with a tool that is fully time based, and they got a very similar result a lot later with a bit more effort. So I was pretty proud of that Monte Carlo simulation that I made really early on in the design phase.
That's cool.
We ended up getting really good results from it, and it was a very simple thing to approach. Yeah, Monte Carlo simulations are super cool. It's kind of this one really crazy thing about it is say you have 1 billion samples, right? You can just, because it's randomly sampled, you can just take 1,000 of those samples and you'll be getting basically the same number, just with less certainty. So you basically just get more samples and you end up with the same number with just more and more certainty the more you add, which is pretty cool. So you can just combine multiple files together. So one thing that I do with this is I'll run it on multiple computers, and they all just like output these text files in parallel, and then I can just like copy paste all the text files together, and I just get a more certain answer, which is really cool. So it's like the most parallelizable computer program you can basically write is these Monte Carlo simulations.
What's the 101? What is a Monte Carlo simulation, like 101?
Oh, a Monte Carlo simulation is the idea of just sampling points and then figuring out like the answer from that sampled point. So my favorite thing is, if you want to show the image, calculating pi with a Monte Carlo simulation. A great way to do that is you have a square that is this kind of background, and then you have a circle in the middle of that, and you want to calculate pi. So what you do is you just randomly sample locations within that circle and square, and then you can divide the area in the circle by the area outside the circle, and it's like pi divided by 4 or something like that. I don't remember if that's the exact answer, but yeah, it's something like that, where it's like you're kind of randomly sampling this space, and because of some rule, you're able to determine like if it's within or without, and then you end up just with like this division problem where you're dividing like one large number by another large number, and you get a very clear answer out of that thing. So Monte Carlo simulations are great when you have a lot of variables that are all kind of working together that are tricky to simulate. So, you use Monte Carlos a lot of times with like fluid simulations, or things where there's like a lot of crazy complicated interactions. And in this case, it's the interaction of like the Earth rotating under satellites that are going in this other dimension. You kind of want to pull time out of that. Like, you don't want to have to know this is like 1 second before this time, this is 1 second before this time. It would be better if you can just like sample thousands of points and not worry about which one happened at which time, because that actually doesn't matter in the simulation. And when you make that simplification, it becomes a lot easier to calculate. One saying that I really like is all simulation is wrong and some is useful. And when you're able to find a simulation that is not very wrong but very useful, that's when you're really kind of onto something. And you always kind of want to look for those opportunities to do something that's very simple, very useful, and very minimally wrong. And in this case, like removing the time component was very minimally wrong. What matters was what the mirror is doing.
Cool. I'm curious. I mean, so that's most of my questions about y'all. I'm curious to hear your other thoughts about what else is happening in the energy world. As a person who's literally built a fusion reactor and a dabble, I'm sure, other stuff as well. Like, what sorts of things are exciting for you? Yeah,
solar is ridiculously exciting. I think everybody kind of gave up on solar a while back because of the variability problem. It's like solar is this thing that you can just put a panel outside and it's going to produce electricity. It almost feels like free electricity. Like, I lived in a van for a while and I had solar panels on the roof, and if you're not using the energy, it's just kind of going to waste in a way. Like, you have a couple hundred watts that you could be using to do literally anything, and if you're not using it, it's there's going to be more tomorrow. It doesn't matter. So it's this kind of like completely different thinking than you get with fossil fuels. With fossil fuels, it's like you burn the gallon of gas, you don't have a gallon of gas anymore. Now you got to go buy another one. And we're kind of operating at that on a human level. Is like everybody's burning these fossil fuels, and it's they're not renewable. They're going to run out eventually, right? And it's there's a lot of issues with like burning a lot of fossil fuels, and there's a ton of fossil fuels out there. Like, we're going to be able to use them for a very long time. But I think the argument I like to make is like, we don't want to have to use them for a very long time. Like, even just driving in your car and running out of gas, it's pretty expensive. Wouldn't it be better if you didn't have to worry about that so much? Wouldn't it be better if it was a lot cheaper? There's this kind of like freedom to having more resource and not worrying about using it. And I think sunlight is going to give people that. I think like when you have energy that you might as well use because it's so cheap, it's going to be a completely different feeling than having fuels where it's like you kind of feel bad about using it. Like sitting in traffic in an electric car feels very different than sitting in traffic in a gas car. So I hear. And yeah, I kind of think we need to move to that as a species. I think also, solar since the 2010s, solar in 2010 was $359 per megawatt. And, today it's like $45 per megawatt, which is just like this unbelievable curve. And there's a couple graphs on this that I can send you of how fast it's gotten cheap.
Oh yeah.
And, everything else has kind of gotten more expensive in that same amount of time. Like natural gas peaker plants, get a little bit more expensive. Nuclear power plants get quite a bit more expensive, $155 per megawatt hour these days. The price goes up because people keep finding new ways that we need to make them safer. And they're pretty hard to make as well. Like the cost of capital goes up a little bit, and it gets very expensive to make a nuclear reactor. On average, it takes 17 to 22 years to go from project inception to actually producing electricity for a nuclear power plant. It's like, it takes decades to build these things, and you have to pay that money up front. So you have to take out a loan, and that loan has to last for 10 or 20 years before you start paying this thing back. And loans like that are really expensive. You're paying a lot of interest in that time, but also it means like a lot of developing nations that don't have access to those kinds of loans just can't do it at all. So France is able to make lots of nuclear reactors there. France has an extremely high nuclear percentage on their grid. But that doesn't work in a lot of countries. It's only something that you can do if you're kind of a richer country that has access to this really cheap capital. I think, in a similar way, fusion is going to have a lot of problems moving forward. It's like, even if fusion was going to work, I think that you're still going to have those issues where you're building this very expensive plant. It takes a long time to do it. Cost of capital is going to be very high, and it's going to take a long time to pay that off. And then solar comes in, and it takes like half a year to a year to build a power plant that can make solar energy. Kind of no matter, the bigger ones take longer, but you hire more people. It's very parallelizable. It's this very fast, very easy thing to do. And, China has absolutely turned on their economic engine. They're cranking out so many solar panels at so much cheaper costs. It's really just this amazing technology that's going to change the world. It just has this problem where the sun goes down every night and they stop working. Everybody says they're really great until the sun stops working. Well, we can fix that. And yeah, I'm super excited about fixing that. And I think there's all these other issues that solar is running into as we add more and more of it. California has this problem with variability. Like the grid is actually pretty expensive to operate and pretty expensive to smooth out. Germany had a huge issue with this as well. When the Ukraine war broke out, it became very clear how dependent Germany was on natural gas. And Germany was like 20 to 30% wind and solar. So they, a lot of their grid was wind and solar powered, and, super variable when you do that. And they got there pretty quickly. They turned off all the coal power plants. They turned off all the nuclear power plants. They just went wind and solar. The problem with that is they ended up burning more natural gas doing that than they did before they installed all the wind and solar. And that's because the kind of natural gas power plants that you use when you have stable energy are called combined cycle natural gas, where you're kind of burning something and then you're using it to spin steam turbines, which are super efficient. If you have a very variable load and you need something that's very fast to respond to that, you need to burn a natural gas peaker plant, which is essentially just an airplane turbine engine that's powering, a power plant. So those are way less efficient than combined cycle gas. So, instead of being $56 per megawatt hour, they're like $170 per megawatt hour.
Jeez.
So Germany ended up needing more of the peaker plant style ones because of all the wind and solar variation. And batteries are kind of around that price point too. They're also very expensive. So it's just like, there's this kind of like ceiling where you can't do more than 20 or 30% wind and solar because it's variable. But with us, we can kind of come in and we can provide sunlight at night and make that solar more like baseload power. So it becomes a lot more similar to like a nuclear power plant or combined cycle gas. And it's not just like more like baseload power, it's like specific baseload power at exactly the times that you need it. Like we can design our satellite constellation to provide sunlight exactly when people need it on the grid, to really help balance out these problems that we're seeing with all these other resources. And I think another big thing is, another question that we get asked a lot is, why not just put more solar in and batteries? Like, why not just add more solar and more batteries? If you build twice as many solar farms as you had before, that's twice as expensive to do. And now you just have more solar panels that are doing absolutely nothing as soon as the sun goes down. So it doesn't matter how many solar panels you have, it does nothing once the sun goes down. In the summer, you get 2.5 times more sunlight than you get in the winter. So if you want your solar farm to last all winter, you have to, basically double the amount of power that's going there. You also have to, essentially double the amount of batteries that are being installed there as well, because now you have to make it through like an 18-hour night instead of like a 14-hour night. So you need way more batteries, way more solar to make it through the winter. And then the summer comes around, and now you have all this extra resources doing absolutely nothing, that you basically just have to turn off, or you get charged money for curtailment. And there's this kind of huge imbalance, because of the way, the seasons work, because of the Earth's tilt and because of the way the Earth rotates. Like you end up with these huge imbalances. One analogy that I really like, that Paul Jaffe said at a talk at a conference is, batteries are like a bank account, and we are just like extra income. And I think that's just like a great analogy for this is like, you can solve some of your problems with a bank account if you have like some cash flow issue or something like that. But what's better is just like having more income all the time that you can rely on. And it costs a lot of money to have that bank account. It costs a lot of money to have batteries. It costs a lot of, they're very expensive to build. It's a lot of CapEx. It's another project that you have to take on. It's another loan that you have to take on. There's all this risk associated with building that infrastructure. And, we can just get away from all of that. You can purchase some sunlight at night. You can see how it works. If you don't like it, you don't have to buy it again. But, we can be pretty sure that you're going to be making power with us. If it costs $50 to buy us and you're able to sell it for $80, it's pretty obvious value. And then, we know on our side that we're making money, at those kind of prices. So yeah, that's the future we're going for is, it's similar to, kind of like what AWS credits did for servers. Like you don't have to build a server farm for, any inordinate number of customers. You can just build, you just buy an AWS credit and that scales with the size of your online business. So this was this huge thing is like now companies didn't have to invest in their own server infrastructure and try to figure out what size it needed to be. They could just buy AWS credits and they would scale to whatever they need. So in that same way, we're able to help our customers because we're able to scale to whatever they need. Say they're one of their farms is underperforming, they can buy a little bit more sunlight, get it back into the realm where they're not going to get a fine for underperformance. And yeah, just give people that flexibility. So there's, when we hop on the phone with solar farms, there's a lot of new uses that we hadn't thought about ourselves.
Sunlight as a service. That's what you're offering. The new SaaS. Awesome.
Sunlight as a service, solar ceiling as a service.
Oh man, there's so many. Okay. I love it. Cool. Well, thank you so much for joining. If there was one place that you could send people, where would you want them to go to either learn more or get in touch with you or anything?
Yeah, our website, reflectorbital.com.
Easy. Awesome. And who do you want to hear from? Do you want to hear from investors? Do you want to hear from people who want to work like dope engineers? Like who do you want to hear from?
Yeah, investors and engineers. You hit the nail on the head.
There we go. Awesome.
So yeah, we're raising money for our seed round right now to launch 2 satellites into orbit to prototype a new form of energy, and we need a team to build that. So yeah, this is like we want to be mass producing these satellites at extremely large numbers, and we want to scale as quickly as possible. And we need capital and a team to do that. So that is my entire job right now.
I love it. Awesome, man. Well, thanks so much for joining. This is great.
All right. Thanks. Thank you, Christian.
Cool.